Hello there, guys. Today we are going to be discussing IB Physics HL Paper 1 from the November 22 examination session. It was a very concept-based paper, in my opinion, but overall, if you guys know your definitions and know some basic rearrangement of formulas, you guys will be amazing. So let's get right at it. Starting with question 1. What is the definition of the SI unit for the force? So the SI unit for the force is a Newton, and we can write out the formula for force. Force is equal to mass times acceleration. So the SI unit for the force is the force required to accelerate in the direction of motion a mass of 1 kg at 1 meter per second. So this is because force is a vector quantity, not simply a scalar, and it must be in the same direction. So these two are obviously incorrect because the weight of a mass of 1 kilogram, that's incorrect, and the change in momentum per second. While this is an accurate representation of what a force is, where F is equal to delta P by T, it is not the SI definition. And when we look at these two, we see the force required to accelerate in the direction of the force, a mass at 1 meter per second. But this one specifies at 1 kilogram. And since we're looking at the exact definition of the SI unit, option A is the correct answer. Moving on to question number 2. A rectangular sheet of paper has dimensions of this and this. We are looking at the uncertainty in the perimeter. So the perimeter is equal to the side length is the sum of side lengths. So you could do this with multiplication, but if you guys remember, multiplication requires percentage uncertainties, and we are given absolute uncertainties. So what we'll do instead is we will stick to addition. So when you have the perimeter, so let's say this is a sheet of paper, this is 30 and this is 20. The perimeter will be 30 plus or minus 0.5 plus 20 plus or minus 0.5. Again, this one, 30 plus or minus 0.5 plus 20 plus or minus 0.5. Now this will give us 100, and since we're dealing with addition, uncertainties will just get added together. So let's put some brackets to make this a little bit easier to understand. So uncertainties will just get added together, and this means that the net uncertainty is plus or minus 2.0. So the percentage uncertainty will be 2 by 100 into 100, which is equal to 2%. Question number 2, option B. Moving on to question number 3. Two forces F and G act on a system. So here we're given a grid and the two forces that are acting on it, acting on the point, this one right here. And we see that F is reversed in direction and G is halved. So let's look at G first. G has a height of 2 and a length of 4. Now, when we halve G, that means it's going to only have a height of 1 and a length of 2. So this is going to be our new vector. Let's call this G dash. Now, I'm just going to pick up this random empty grid, so that we can represent how our new vector is being formed. So let's draw out G dash, which is right here, G dash. And now let's look at F. F is reversed in direction, and F is 5 units long. 1, 2, 3, 4, 5. Is that right? Yep, that is F. So now let's look at the resultant vector. We know it has to be up because there's really nothing pointing downwards. So let's cross this out and let's do some subtraction. So this is 5 and this is 2. So that means the final vector is going to have a magnitude of 3 in the negative x direction. Next, if we do some addition here, we have a 0 in the y axis for force F, and for force G dash, it is 1 in the positive y direction. This means that we have a plus 1 here. So let's draw this out. Plus 1 here and minus 3. 1, 2, 3 right here. So if we match these grid points up, this is our new vector. So let's see which one matches this vector. Option A is incorrect, option B is incorrect, option C is incorrect, and option D is the correct answer. Let's go ahead and move on to question number 4. Ball 1 is dropped from rest at a height h. Same instant, ball 2 is launched vertically upwards with an initial velocity u. So when we're looking at the time at which both balls are the same height above the ground, this is where we have to consider some mechanics, a lot of mechanics actually. This is the classic mechanics question that's present in every IB paper, and usually these are the hardest questions because they require the most critical thinking. So when we go ahead with this, we have, so how about this? For ball 1, let's say the distance that it's covering downwards to be delta S1, which is equal to minus half into gt squared. Now this comes from the equation S is equal to ut plus half at squared, where u is equal to 0 for delta S1 because the ball is dropped from rest. So this gives us S is equal to half at squared, and since A is equal to gravity and it's pointing downwards, minus g. So delta S is equal to minus half gt squared. Now let's look at the height that the ball will be at any instant. So let's call this h1, and this will be h minus half gt squared, because this is your initial part, right? H, this is your initial height, and in time t, it moves down by this much. So to find this height, it moves by this much, which we call delta S. This height right here will be h minus delta S1. So that is your first height. Now let's look at ball 2. Looking at ball 2, you see that we can again apply the same S is equal to ut plus half at squared formula. Except this time we have initially upwards with the velocity of u. So S is equal to ut minus half gt squared, because once again you have gravity acting downwards, causing it to move downwards, causing the acceleration to be downwards. So since ball 2 started from the origin with h is equal to 0, that means it only moves up, and h2, the height that ball 2 is at any given point, is ut minus half gt squared. Now let's look at exactly what the question wants. When are they the same distance above the ground? This means that at a particular time t, which is this, both h1 and h2 are the same. h1 is equal to h2. So if you write this out, h minus half, oops, half gt squared is equal to ut minus half gt squared. So if we were to cancel, half gt squared get cancelled, and now you have h by u is equal to t. Question number, yes, ut is equal to h. Let's write this step out. T is equal to h by u. So at this time, both walls are the same distance off the ground. Question number 4, option C. Question number 5. The diagram shows the trajectory of a projectile with launch at velocity v. But here's the kicker. Air resistance acts on the projectile. This means that at any point, due to the velocity of the body, it experiences a force in the opposing direction, similar to friction, except this is more like air friction. So let's call this force Fd. Now, for those of you who are familiar with air resistance, you would know that Fd is equal to half CD rho A V cubed, V squared, sorry. And this isn't exactly important, but it might help visualize some of the next parts. So let's go ahead and look at the horizontal component of acceleration. If this is our body, let's leave, yeah, if this is our body, we have our air resistance acting this way. But in reality, because air resistance is the proportional to velocity, it means that it's actually acting this way. So it forms an angle theta to your x and y axes. Let's call this theta. As such, your horizontal force will be greater than 0. So it's a non-zero quantity. And this will be Fd cos theta. Now let's look at our vertical components. The projectile has a mass m, so it will be pulled downwards with a force mg. Now let's just change colors here real quick to make it a little bit easier to see. You also have the component of drag force, and because it's at an angle, you have this Fd sine theta. So your Fy, the net force in the y-axis, is equal to mg plus Fd sine theta. This means that the acceleration in the y-axis is equal to g plus Fd sine theta by m. Now, this immediately means that the vertical component of acceleration is greater than 9.8 meter per second squared because of this Fd sine theta that is present. This is a tricky one, guys, so watch out. Up next, going on to question number 6. An object of mass 2 kilograms is on a horizontal surface, and it is pulled by 12 newtons, accelerating at 2 meter per second squared. What is the coefficient of dynamic friction? So let's go ahead and draw out a free body diagram and see how this works. This is your gravitation force, mg, your normal reaction force, which is also equal to mg because you have no vertical acceleration. Next, you have your forward 12 newtons, and you have your backward friction, which is equal to mu mg. Now, if we write out our different values, m is equal to 2 kilograms, a is equal to 2 meter per second squared, and F is equal to 12 newtons. So let's go ahead and figure out how this works. If this is our net force, F net, there are two forces that make it up. F, which is our pulling force, and subtracting from that, friction, or frictional force. Let's write out F net as m times A, which is equal to 12 newtons, minus mu, which is unknown, m, which is 2 kilograms, and g, which is, for this example, let's call it 10. And let's go ahead and write these values out as well. 2 kilograms times 2 meter per second squared. So 20 mu is equal to 12 minus 4. Mu is equal to 8 by 20, equal to 2 by 5, equal to 0.4. Therefore, question number 6, option B is the correct answer. Moving on to question number 7. A person lifts a total mass of 20 kg through this distance, and it's performed n times to transfer this total energy. Now, one thing you guys will have to know in physics paper 1, you need to know pretty much every formula in the data booklet by heart. You can get away with forgetting the chapter 8 formulas and referencing them in the middle of the exam, but you need to be way faster than what I'm doing right now. The number of problems you'll have to do beforehand to get a feel for this might be huge, but if you really want a 7 in physics, a significant amount of work has to be put in. Work. So right here, this question uses a bunch of basic formulas. Work is equal to force into displacement, and this total energy is the same as saying this much work has been done. And the force, the downward force that's acting, is mass times gravity, because work is done against gravity because it's being lifted up to a vertical distance. So let's write this out. Work is equal to mass times gravity times distance. And since it's done n times, we can write it as work is equal to n times mass times gravity times distance. Let's write in our values. 6 into 10 power 4 joules is equal to n times mass, which is 20 kilograms, times 10, which is gravity, times s, which is 0.6 meters. So let's cancel these two, make it 6. And let's cancel these two, make it 1. So n is equal to 10 power 4 whole divided by 20. This essentially means you have 1 by 2 into 10 power 3, which is equal to 500 times. So question number 7, option C is the correct answer. Moving on to question number 8. An engine is exerting a horizontal force F on an object, and it's moving along at a constant velocity v. Know that when you have a constant velocity, there is no acceleration on the object, which means that your friction, or your force, is equal to frictional force. This might make more sense if we were to draw out a diagram. Let's pick a different color for this. So, looking at that, here we have our force that's acting on it. Then we have frictional force, weight, and your normal reaction force. Since the force and frictional force are the same, you can say F is equal to F, which is equal to mu n. And n is the normal reaction force, which in this case is equal to mg. So F is equal to mu mg. Now let's look at another formula. Power is equal to force into velocity. This is straight from the data booklet, guys. I'm not going to derive it here, but it's a very helpful formula, especially in cases like this. This means that your power is equal to force times the velocity that's moving at, which is v, which is mu mg v. Question number 8 is option D. Moving on to question 9. A model rocket is launched from rest. The graph shows the variation of force against time. What is the maximum velocity reached by the rocket? So the units of force is kilogram meter per second squared. The units of momentum is kilogram meter per second. You notice how these two differ only by a second. So if you multiply it by time, you get momentum. Now let's look at this. If we're trying to find the maximum velocity, we have to find the maximum momentum. And this can be found using the area under the graph. So let's go ahead and split up the area of the graph into two parts, part A and part B. So in part A, we have an area of half to 0.5, which is half, into 20 newtons, which is equal to 10 5, equal to 5 kilogram meter per second. Next, in area B, we just have a rectangle. So this is 1 second times 10 newtons, which is 10 kilograms meter per second. So your net momentum, your net final momentum is 10 plus 5, which is 15 kilogram meter per second. Now let's go ahead and look at the mass of the rocket, 0.2 kilograms. So momentum is equal to mass into velocity. Therefore, velocity is equal to momentum by mass, 15 by 0.2, which is equal to 15 times 10 by 2, which is equal to 75 meter per second. Question number 9, option C is the correct answer. Moving on to question number 10. The temperatures of the same liquid are mixed in an insulated container. What is the equilibrium temperature of the mixture? Meaning, what is the net temperature of the mixture once all of them are mixed together? So there are two ways to solve this. Both are essentially the same thing. You see that this is at the highest temperature, so any heat, which is energy lost by this, is gained by these two. So we can write this as E1 or delta E1 is equal to delta E2 plus delta E3 because of the conservation of energy. We'll assume that no energy is lost to simplify things. Now let's use the formula E is equal to mc delta T. So here we have 2m C, and let's assume our final temperature is T. So m C and delta T will be 60 minus T, which is equal to 2m C, and here our final temperature is going to be higher than our initial, so 30 T minus 30 plus m C T minus 0. Let's go ahead and cancel out some variables. Constants. M and C are constants for this particular setup. So you have 120 minus 2t is equal to 2t minus 60 plus t. Rearranging gives you 180 is equal to 3t or 5t, sorry. And t is equal to 36 degrees Celsius. Let's move on to question number 11. Gases in the atmosphere comprised of these three compounds. Which sample contains the greatest number of molecules, given that all of the samples of these four gases have the same mass? So for chemistry students, this might be a pretty dead giveaway. Number of molecules is equal to Na times moles. And of course, for physics students, this should be pretty familiar as well, but if you've done both, this might be really easy for you. So this means that the number, I'm just going to write number from now on, is directly proportional to the moles. And the formula for moles is equal to mass by molecular mass. For each of these, the molecular mass is given by adding these mass numbers. So let's write it right on top. So this is 12 plus 32, which is 44. N2O, which is 28 plus 16, which is once again 44. 12 plus 4, which is 16. And 2 plus 16, which is 18. Now, the number of moles is inversely proportional to the molecular mass of the compound. This means that the lower the molecular mass, the greater the number of moles. And since we're looking for the greatest number of molecules, the number is inversely proportional to the molecular mass. So we're looking for the lowest molecular mass compound. That would be CH4. Question number 11, option D. Moving on to question 12. This is a purely theory-based question. KB has a unit of joules per Kelvin. This is correct since KB, the Boltzmann constant, is equal to the Rydberg constant, which is the gas constant 8.31, divided by Na. So both of them have the same units, which means they have a unit of joules per Kelvin. Next, like I said right there, this is correct. And looking at the final one, KB is equal to the average kinetic energy of the particles divided by the temperature of the gas. This uses the formula Ke is equal to 3 by 2 kBT. Now, I want you guys to look at something. Here they've not said that Kb is proportional to the average kinetic energy of the gas. Instead, they've simply stated that it's equal. This means that this statement is incorrect because while Kb is definitely proportional to the average kinetic energy by temperature, it is not equal. Therefore, the correct option for question number 12 is A. Moving on to question number 13, we are looking at a mass spring system. And we're trying to find the position that the object has zero velocity and a negative acceleration. So I'm going to pick out two colors for this. Yeah, sure, that should work. So let's go ahead and draw the VT graph. So velocity is essentially the differentiation of the position curve for those math students. You guys should know this. Oh, that was a terrible curve. So yeah, velocity is proportional is the differentiation of this curve. So we end like this. So this is a velocity curve. Next, we're going to take a look at our acceleration curve, which is essentially a flip of about the x-axis of the position curve, also known as the differentiation of the velocity graph. So when you look at this, it's a pretty bad graph, I know, but let's go ahead and find the places that the object has zero velocity. Position A and position C. A little bit wonky, but you get the point. Now, let's look at where it has a negative acceleration. This means that the purple graph must be below this line. The only point that's there is between here and here. And the point where both conditions are satisfied is point A. Question number 13, option A. Next, a sound wave travels through a gas at a speed of 270 meters per second. The displacement of the gas with a distance d from the source is given in the graph. They're asking us to find the frequency. So when we're looking at a displacement versus distance graph, the wavelength is pretty much the same as you would expect on a normal distance time graph. The only thing is you need to find this as the wavelength, because the wavelength is the amount of time it takes from the compressions to expand out and go back to compressions once again. So that means that this is one wavelength right here. So if we take this distance, which is 1.5 meters, and we take our speed, which is 270 meters per second, let's use the v is equal to f lambda. So 270 is equal to f times 1.5 meters. So f is equal to 270 by 3 by 2. 540 by 3, 180 hertz. Again, quick maths is pretty effective when you are doing physics HL especially. So get those numbers in, guys. Otherwise, it's going to take a while. Let's look at question number 15. A point source emits a sound wave of amplitude z, distance l, and the amplitude is changed to 2z. What distance must the person move? So they're not asking what is the distance between the source and the person. They're asking what distances they have to move through to hear the original intensity again. So let's write out some formulas. Intensity is proportional to amplitude squared, and intensity is also equal to power by 4 pi r squared, which means that intensity is proportional to 1 by r squared. So if we put together this one, let's call this 1, and this one 2, we get intensity is proportional to amplitude squared by distance squared. So if we have a point source emitting amplitude z at a distance l, your intensity is going to be z squared by l squared. Now when this becomes 2z, when this becomes 2z and this comes here, this is now the distance that it has to go through, and intensity must still be z squared by L squared. But because you have this as the amplitude, you have 4z squared by 4L squared. How do you find this? Simply by comparing the equations. 4z squared by L naught squared is equal to z squared by L squared, cancelling out the z squared. L naught squared is equal to 4L squared. So, so your final distance, which is L naught, is equal to square root of 2 of 4L squared, which is equal to 2L, which means that the distance it must travel is 2L minus L, which is equal to L. Question number 15, option A. Question number 16, this is where we start moving into drift velocities in currents. We have two copper wires of equal lengths but different diameters, and they're used to connect a cell to a load. So if we were to draw this out, yeah, we get a battery here, and your first wire here, and your second wire here. Now, each wire has different properties, but they have the same length. Wire 1 has a diameter of m, and wire 2 has a diameter of 2n. The electron drift velocities, Vd, in wires 1 and 2 are given here with these symbols. What is the ratio from a V2 to V1? Let's go ahead and look at this. I is equal to NAQV. Now, this means that V is equal to I by NAQ. Now, for the particular instances that we're taking, we have two different areas. A1 for wire 1, which is equal to pi by 4 times m squared, and A2 is equal to pi by 4 times 4m squared, which is equal to pi m squared. Now, since these are connected in series, the current is the same for both of them, which means that NAQV1 is equal to NA2QV2. Now, N and Q are constants in these two expressions. Now, obviously, this is because they are made of the same material, copper wires, which means that they have the same number of charges per unit volume, and they have the same charge on each of their mobile charges, which is 1.6 into 10 mod minus 19, because they conduct via free electrons. This means that V2 by V1 is equal to A1 by A2. So if we write this out, you get pi by 4m squared by pi m squared. Cancelling, V2 by V1 is equal to 1 by 4. Option D is the correct answer. Question number 17. A cell of negligible internal resistance is connected to three identical resistors. The current in the cell is 3 amps. They're now in series. What is the new current in the cell? This particular arrangement gives us a net resistance of 3R by 2, since this gives R by 2 and this gives R, and that gives you 3R by 2. Now, when they're arranged in series, you get a net resistance of 3R. So when you have 3R, let's say this is V. So V is equal to IR. Here I is 3 amps. So V is equal to 3 times 3R by 2. V is equal to 9R by 2. The voltage of the cell does not change. So if we were to rewrite this, 9R by 2, in the new setup, we have I dash times 3R. Let's start cancelling. RR, I dash is equal to 1.5 amps. This means that the answer to question number 17 is option B. Question number 18. This requires knowledge of Fleming's hand rules. Here, Fleming's left hand rule. So when you have the left hand rule, you have three fingers: your thumb, which gives you your force, your index finger, which gives you your magnetic field, and your middle finger, which gives you the current. So when you align these three according to the diagram, you see that current is going this way and magnetic field is going into the paper. This means that force is moving outwards like this here. Now, as you travel around the loop, drawing out the forces, this means the loop is being stretched outwards, thus increasing the radius of the loop. Question number 18, option D. Moving on to question number 19. This is one of the most equation heavy, or rather mechanically intensive questions, where you really have to think before doing anything. Right here, the mass is swung in a circle of radius r, and another mass is held here, stationary. The tension in the rope keeps this mass from moving. So this means that your centripetal force here, m omega squared r, is equal to this mass here, mg. Now we are using this m omega squared r instead of mv squared by r because we have the time period for the rotation. And time period for rotation can be converted to omega by dividing it with 2 pi. So let's rewrite this. M times 2 pi by t whole squared times r is equal to mg, sorry, long m, m 4 pi squared m r by t is equal to mg. Now here's the ratio they're asking for. M by m is equal to 4 pi squared r by g. Now here's where the math gets a little bit mathy. Let's go ahead and find out the value of pi squared. 3.14 by times 3.14 gives 651241321496958 and 4 decimal places, 9.8596. Can you round this up to 9.86? That looks kind of familiar, doesn't it? The value of g over here is 9.86 meter per second squared. So this means that m by m is equal to 4 times 9.86 times 0.25. T squared is 0.25 because 0.5 whole squared is 0.25. 0.25 times 9.8. Let's cancel these out, and this gives you a final value of 4. Question number 19, option C. Now you guys may have noticed that I'm solving this in the actual exam pattern. I haven't solved this, or I have solved this paper before, but without any calculator, without any solutions by my side. I am solving this as I would in the exam paper, just a little bit more detailed and a little bit slower so that everybody understands. Let's look at this question. You have two planets, two bodies, and you have a point where the gravitational fields cancel out. Here, G is equal to Gm by r squared. Now, I know a lot of people that can get confused between gravitational potential, gravitational field, electric potential, electric field, so on, so on. So what I like to do is gravitational potential, all these potentials are always scalar, so they always add up. You can never have them cancel out like this. This means that the only possible one here is G is equal to Gm by r squared. Now, let's look at what happens at point X. G Earth is equal to Gm. So Gm, which is m Earth, Gme by r squared, which is d squared, is equal to Gm, which is the moon's gravity. So Gmm by d minus d whole squared. Now at x, when we cancel, we get me by d squared. So this one, not these two, d minus d whole squared, not this one either. Question number 20, option C is the correct answer. Question number 21, the unified atomic mass unit is a non-SI unit used to state atomic masses. This is another theory question, which is this. It is 1/12 the mass of a carbon-12 atom. Question number 21, option D is the correct answer. Moving on to question number 22. This requires knowledge of decays, electron decays, or atom decays. So here we have U-237 being converted to U-233. Now I have no idea what the mass or the atomic number of uranium is. You might, but in this case you'll find that it's irrelevant. Since it's the same element, the same atomic number must be present. So any changes made to the atomic number must be 0. Now, all of these have an alpha particle involved. So let's see what happens when you have an alpha particle. An alpha particle has a mass number of 4 and a atomic number of 2. This means you have a -4 in mass and a -2 in atomic. So what happens when you have this -4? You immediately get the correct value here, but your atomic number has been changed. This means that you need to add this back up using beta minus decays. A beta minus decay has 0 minus 1, so no change to mass, but it has a +1 change to atomic. So to cancel out the effect of this, we need 2 beta minuses. So let's look for the option that has 2 beta minuses and 1 alpha. 2 beta minus, 1 alpha. Question number 22, option B is the correct answer. Question number 23. Which of these constituted a paradigm shift? Theory of knowledge in physics. I know, guys, sometimes it's not fun, but it is necessary in questions like this. Here, the only real answer is E is equal to mc squared. A very famous equation, and I know in the heat of the exam, you might forget it, but if you really think about it, classification isn't that big of a thing. Determination of velocity of light, no. Maybe the wave slash particle duality might have constituted, but not the velocity of light, which is refraction. Next, the equation of F is equal to ma is again wrong. Question number 23, option D is the correct answer. Question number 24. A very interesting question in my opinion. We have a fusion reaction of a nucleus of hydrogen 2 and a fission of uranium-235. These are the two masses. They're asking for the ratio of specific energies. So specific energies has a unit of joules per kilogram. So, and the energy is given by this E is equal to mc squared formula, where mass is directly converted to energy in these fusion and fission reactions. So let's go ahead and find out how this works. Since we have 0.19 U, E is equal to 0.019 U C squared for the first reaction, and E is equal to 0.19 U into C squared for the second reaction. So let's leave the C squared in U because we're looking at a ratio, so they'll get cancelled out anyways. The specific energy is the energy 0.019 U into C squared divided by the mass. So let's call this phi U because this is deuterium H21 and tritium, which is H31. So the total mass is 2 plus 3, which is 5, whole divided by 0.19 U times C squared divided by 235 U. Now you'll notice that the light cancels out. 0.019 divided by 0.19 times 235 whole divided by 5. This gives us 1, 10, and 47, which gives us 4.7, which is approximately equal to 5. Moving on to question number 25. Water is pumped through a vertical height of 12.5 meters and wind blades are sweeping this area. The area of the blades is 100 meter squared, and the average wind speed is 5 meter per second. What is the maximum mass of water that can be pumped every second? This uses your energies, guys. So chapter 8, you'd want to use the data booklet for this because there's a formula that I particularly don't like to memorize. If you do, go right ahead. So let's write out what we have. We have an efficiency, which is 50%. We have the area of the blades, which is 100 meters squared. We have the density of the air, which is 1.2 kilogram per meter cubed. We have the velocity, which is 5 meter per second. And finally, we have the delta H in water, which is 12.5 meters. This means that your power in a wind turbine is half rho a v cubed. This is from the data booklet, guys, so you can use it straight from there. But since you have an efficiency of 50%, you can multiply it by your efficiency constant. Here I'm just using the Greek letter eta, I believe, but it just looks fancy, doesn't it? So let's go ahead and find the power output. Half, and this also half. So let's put that in the beginning. Rho is 1.2, A is 100, and V cubed, which is 125. 0 0.6, 0 0.3, 30 times 125, which is equal to 3,750 joules. Perfect. Now, your power is also equal to energy by time. So, since we have the water being moved through a vertical height, we have a delta E. So, let's write this as delta E. So, in every second, so let's say t is equal to 1, your power is equal to your change in energy. So, 3,750 joules is equal to delta E, which is m, so mass, which is given as m times g, let's call this 10, h, which is 12.5. So now if we cancel out, you will find that you have 30 over here. So m is equal to 30 kilograms. Question number 26. The electromagnetic spectrum radiated by a black body at a temperature T shows peak at wavelength lambda p. What is the variation of lambda p with respect to T? So this is another direct data booklet question. If you look at your section 8 with the chapter 8 formulas, you find that lambda p or lambda peak is equal to 2.90 into 10 power minus 3 by T, which means that lambda p is proportional to 1 by T. Now, you might be tempted to select this, an example of Wayne's law, but you should remember this is not lambda p, this is intensity, and this is lambda. So you would find at different temperatures the peak wavelength is changing. That was a terrible graph. So on. So for question number 26, option A is the correct answer. Moving on to question number 27. A ray of white light is normally incident on a thin layer of oil on water. The refractive index of oil is 3 by 2 and the refractive index of water is 4 by 3. Now, for this particular question, you need to know total internal reflection and thin layer interference. Not total internal reflection, thin layer interference. And for that, I would suggest a video by Chris Stoner. It is absolutely spectacular, and I'll link it below in the comments. So here what you're looking at is air, n is equal to 1, oil, n is equal to 3 by 2, and water, n is equal to 4 by 3. So if you think about it, when you move from a more dense to a from a less dense to a more dense medium, you are going to have an inversion of your ray. And like I said, the video that I link below has really explains it really well. But when you go from a less dense, from a more dense to a less dense medium, you do not have the same inversion. So for the same for this particular incident, this particular situation, you have only one inversion of light, and that is present at the air-water boundary. So this means you use the data booklet formulas. If you were to have 0 or 2, you would have to swap around the data book formulas. So for constructive, the formulas that is given is 2dn is equal to m plus 1 by 2 lambda. Now here m is just any constant, and since we're looking at the minimum thickness, the minimum constant m can be 0. So 2, and d is your thickness, d. N is the refractive index of the medium, which is 3 by 2, is equal to 1 by 2 into lambda. And here lambda is lambda v. So let's cancel some things out. We get d is equal to lambda v by 6. Question number 28. A telescope can just resolve images that are separated by an angle of 2 into 10 power minus 7 radians. Now, the two stars are given at a distance of 4 to 10 power minus 6. They're asking the maximum distance between the stars and the telescope for the images to be resolved. Now, for this, what we're going to do is we're going to draw out a triangle. Let's take this to be star 1 and this to be star 2. And let's call this our home, planet Earth. When we take these distances, and we draw out a triangle like this, we get that this is 4 into 10 power minus 6 meters, right? Now, this angle is 2 into 10 power minus 7 radians. But if we're looking at the distance between the stars and the telescope, we are looking at this distance. So let's call this phi. So phi is equal to 1 into 10 power minus 7 radians. And you need to take this distance. You can't just take the whole distance, which is 2 into 10 power minus 6 meters, or 2 into 10 power 16 meters. Now let's use tan theta. So tan phi, because we have our adjacent, which is, we need to find our adjacent, which is this. Let's call this x. And we have our opposite, which is this. A little bit of trigonometry should give you the right answer, which is opposite. So 2 into 10 power minus 6, 2 into 10 power 16 divided by x. Sorry, I keep clipping over my words today. So x is equal to 2 into 10 power 16 divided by tan of 10 power minus 7. Now, here's a very special case. We can use something called small angle approximation, where tan theta is equal to theta for such small angles on the order of 10 power minus 7. And you can enter this into your calculator and actually find that it's very, very, very similar. But because you're in the exam hall, you can just write 2 into 10 power 16 divided by 10 power minus 7, which is equal to 2 into 10 power 23 meters. Question number 28, option C is the correct answer. 2 into 10 power 23 meters. Question number 29, a very interesting question in my opinion. It uses a combination of formulas, and there's two ways to do this. One is to know the baseline formula upon which every single Doppler's effect question is created, which is f dash is equal to f v plus or minus v observer by v plus or minus v emitter. And going from here, we can solve this. And v observer is 20, v emitter is 40. And because the relative velocity between the two is just 20 meters per second, because if we were to consider this to be still, this would be moving towards it at 20, like that. We'd find that the velocity of the, we'd find that the frequency f dash is going to be greater than f. So this will be minus and this will be minus. But let's go through it step by step and try to find out how this would work. So let's go ahead and consider what happens if the object or the receiver is stationary? F dash is equal to F that's emitted into V by V minus 40. This is going to be your frequency that is heard by a stationary observer. Now, what happens when you factor in the moving observer? So let's say that the frequency that's now being heard is F dash, or emitted is F dash. So let's call this F double dash is equal to F dash times V minus 20 by V. So let's solve for F double dash. F double dash is equal to F into V by V minus 40 times V minus 20 by V. Cancelling out, get option A. F double dash is equal to F V minus 20 by V minus 40. Question number 29, option A is the correct answer. Moving on to question number 30. So in this question, we have a capacitor, or we're considering a capacitor, in which the edge effects are negligible, and we're asked three things about it, and we have to find out which are true and which are not. For a capacitor, the field lines within a capacitor are perpendicular to these surfaces, so they're like this. However, close to the end of the capacitor, what ends up happening is that, the field lines begin to curve up and around. Now, this may be something you studied, something you may have forgotten, but it's okay because, lucky for us, we are neglecting that. So, with that diagram in mind, let's look at this. The electric field strength between the plates is Q by CD. So, electric field strength, E, is equal to KQ by R squared. Now, V, the electric potential between them, is KQ by R. These are formulas from the data booklet. So, V by R. And since you have R is equal to D, we write V by D. But what about Q by C? Let's look at the formula for capacitor. Q is equal to CV. Therefore, V is equal to Q by C. This means that E is equal to Q by CD. Option number 1 is definitely correct. Up next, electric field lines are at right angles to the plates. Like I said here, these field lines are at right angles to the plates. Only because of the edge effects would they not be, but because we are ignoring them, so our statement number 2 is also correct. Next, we're looking at the equipotential lines. So generally within the capacitor, the equipotential lines are straight. But as you go out, they follow these edge effects into these curved paths. But because we are ignoring edge effects, equipotential lines are parallel to the surface. This means that option D is correct, where 1, 2, and 3 are all true. Question number 30, option D is the right answer. Moving on to question number 31. An electric field is established between two electrodes separated by a distance d, held at a potential difference of V, and a charged particle in this field experiences a force F. Now, here let's just start plus minus just for convenience. But let's write out what force means. F is equal to KQQ by R squared. And let's write out the formula for potential, which is really what you're considering. Anytime you have a capacitor, you're going to consider the potential between the plates, because that leads to a lot of important values. So right here, you write out V is equal to KQ by D, and F can also be written as VQ by D, since this D and this R squared get cancelled out. Now we are looking for the charge on the particle. This means that charge is equal to force into distance divided by potential. So Q is equal to Ft by V. So which answer is that? Option D. Question number 31, option D is the correct answer. Next, we move on to question number 32 with satellite motion. So let's go ahead and draw a quick diagram for this. Use black. So if this is the planet, we have two orbits, one of X, which is closer to Earth, and one of Y, which is further from Earth. So these will orbit in, let's call them circular orbits, although in reality, elliptical orbits take precedence in this universe because of stability. Now that's a whole other story. But for now, we will consider these two satellites, X and Y. So we are asked a few parts. We are asked a few things. First of all, the orbital periods, and second, the total energies. So here's where, let's start with orbital periods. The Kepler's law states that t squared is proportional to r cubed. Now there's a whole formula behind this, but this relationship is the most important. You may be asked to derive the entire equation, but for now we'll just use this relationship. T squared is proportional to r cubed. And since Rx is less than Ry, Tx is less than Ty because they are directly proportional. Next, we'll move on. Well, let's mark that out. Ty is greater than Tx. Next, we'll go on to total energy. Now, the formula for total energy should, in theory, be memorized, but you don't have to memorize it. You can add together the potential and kinetic energies and find out how that goes using formulas from the data booklet. Kinetic energy will be half mv squared, potential energy similarly. So total energy is minus gmm by 2r. Now this means that total energy is inversely proportional to minus 1 by r. Now this is where most students get confused. We might just consider total energy inversely proportional to r, but because we have a negative symbol, it changes things up a little bit. So, like we said, Rx is less than Ry, which means that Tx, the absolute value of total energy of X, is greater than the absolute value of total energy of Y. But because there's a negative sign, Y has a greater total energy than X, since a smaller negative value lies closer to 0 on the number line than a larger negative value. So, some confusing stuff that IB loves to trick you with. Keep your heads in the game, guys. So question number 32, option D is the correct answer. Moving on to question number 33, a resistor connecting two parallel conducting rails with a distance d apart. Conducting bar is rolling along a magnetic field of 2 Tesla. So let's think about what formulas we can use. First of all, let's find out what we're looking for. We are looking for the velocity, v. So for convenience, I'm going to write v like this with a gamma symbol because I don't want to mix up v and v. So to find our velocity, we need to think about a few things. Let's just write out a formula that's in the data booklet. EMF is equal to BVL. Now, our velocity is what we're looking for, and we have a graph of V, which is voltage, essentially EMF, and L, which is the distance between the bars, L. So we have a straight line, which means that it's y is equal to mx plus c. Now if you would ignore this plus c simply for the sake of simplicity, we see that x is equal to L and m is equal to b into velocity. So to find out the velocity of this bar, we are going to find the slope of this line. which is b into velocity. Let's go ahead, and whenever you're dealing with graphs, find 2 points that exactly coincide with the lines as best as the eye can see, and use those two regardless of how far apart they are, because I guarantee it'll be easier than estimating 0.5. So let's look at the height, which is 3, 6. So this is 3, a gap of 3 volts, and the run, which is 0.5 meters. So you have 3 volts by 0.5, or 3 by 0.5, which is the slope, is equal to B, and B is given over here is 2 Tesla times your velocity. Now, when you do this, you end up finding that this cancels out to 6 and these cancel out to 3. Pretty nice. So velocity is equal to 3 meter per second. Question number 33, option B is the correct answer, 3 meter per second. Moving on to question number 34, which is a pretty simple question of mutual inductance. We see that the switch is initially closed. This is a very important step because sometimes they say it's open, but in reality, it doesn't really change that much. Since it's closed, the ammeter reading before T0 is 0 because there is no changing magnetic field. Let's let that out. No changing magnetic field. This means that there's no induction in this coil, and that means there's no current running through the wire. Now, the second the switch is opened, the magnetic field falls. Let's say it's here, suddenly it goes down here. And this change over here causes a increase, or cause a peak, and then it starts falling down again when it goes back to the same level. This means that a peak will occur before falling back to 0 in the EMF, which means that the current will also go to a peak before falling down. Question number 34, option A is the correct answer. Moving on to question number 35. What is the purpose of using a step-up transformer at a power station? So here's a very basic real-world application kind of question. You know, power is equal to I squared R, and when you step up, a step-up transformer increases the voltage but decreases the current since power is conserved. This means that voltage is stepped up, not the current, so these two are incorrect. And when you increase the voltage, you decrease the current. That means since power is proportional to I squared, a decrease in current will decrease the power loss. So energy loss is decreased. Question number 35, option C is the correct answer. Question number 36, a student states 3 facts about the time constant in a capacitor resistance circuit. Now, for this, I like to keep the graph handy. You will need to memorize this because it's actually pretty important to know and very helpful in most cases. So here we have a voltage time graph, and here you have the voltage in a discharge curve and voltage in a charging curve. So this is a pretty bad graph, but bear with me here. This, or I guess, would be another value exactly. This, let's say, corresponds to 0.67632 V, where V is the initial voltage, and this corresponds to 0.37 volts, where V is the initial voltage. Now, this formula stems from the formula in the data booklet. These constants stem from the formula in the data booklet, which is C is equal to, or rather V is equal to V naught e power minus tau by T, like that. So this means that the time required for the capacitor to be charged through the resistor to a voltage of 0.632 volts is correct. This gives us the time constant. because this time t is the time constant. Next, we're looking at the second one. It's a discharge. Low voltage is 0.62. No, we're looking at 0.37 volts here, which gives us this value. So this is incorrect. Next, in the data booklet itself, we see tau is equal to RC, which means that the third statement is correct. Question number 36, option B is the correct answer. Question number 37. This is photoelectron ejection from a metal surface using the formula Ke is equal to Hf minus phi. So the threshold frequency is F. This means that for 0, Hf minus phi gives 0 kinetic energy. So phi is equal to Hf. Now let's look at this. When radiation of frequency 2f is incident, the kinetic energy of the photoelectrons is K. So 2hf minus hf is equal to K. K is also equal to hf. That's pretty good, because what you now have is you have 4hf minus hf, the work function, is equal to K dash. 3hf is equal to K dash. K dash is equal to 3K because of this. So your final answer for question number 37 is option C. Moving on to question number 38, we are in the final stretch, guys. I'd like to repeat that in the actual exam, you will need to solve questions way faster in order to keep at least 15 minutes of checking time. 1 minute per question is your goal. If you hit that, you are on track to at least hit a 6, guys. So we have three equations related to atomic and nuclear physics. Minus 13.6 n by n squared, electron volts, is the energy. Next is n is equal to n naught e power minus lambda t, which is nuclear decay. And this is angular momentum, quantization of angular momentum, I should say. So let's write those out. Quantized angular momentum, nuclear decay, and energy of orbitals. Now, what's important here is the question, which one's the first Bohr model of hydrogen? If we think about it, nuclear decay has nothing to do with the Bohr model of hydrogen. This one and this one definitely too, because Bohr proposed the quantization of angular momentum to show why the electron orbitals do not just collapse upon themselves, and he gave the energy of a hydrogen-like orbital. Question number 38, option 1 and 3 are correct, which gives you B as the final answer. Question number 39, which emission shows a continuous spectrum? So this is a very common question that you guys might know, and option C is the correct answer, but let's just go ahead and look at it. From nuclei shifts, they are at distinct levels, which means that they will not have a continuous spectrum. Photons during energy transitions, again, we have this formula, which means that they cannot be continuous because you have n is equal to 1, 2, 3. So this is also incorrect. Finally, we look at alpha particles. Alpha particles are also incorrect because they share energies, and mass conservation is important here. So option C is the correct answer for question number 39. Question number 40. The nucleus of the isotope hydrogen-2 has radius r and density rho. What is the approximate radius and density of nucleus of oxygen-16? A very important thing to note is the density of the nucleus always remains the same, since the constituent particles are always the same. However, we must use the formula that is given in the data booklet. R is equal to R naught a power 1 by 3 to find the answer. So let's write it out for hydrogen 2. So for hydrogen 2, R is equal to R naught 2 power 1 by 3 cube root of 2 times R naught is equal to R H. Now let's look at R oxygen. So for RO16, we have R naught into 16 power 1 by 3, which is equal to 8 into 2 whole power 1 by 3 R naught, which is equal to 2 cube root of 2 R naught. Now, if you compare R oxygen and R hydrogen, you see that RO16 is equal to 2 times RH. So the radius of oxygen 2 is 2R. Question number 40, answer is A. And that completes the question. That completes this paper, guys. I hope everything made sense and you guys were able to understand all these questions pretty well. If you have any questions, please leave them below in the comments. And if you'd like me to do any future papers or you have any requests for topics or particular questions, feel free to leave them in the comments below and I'll see what I can do. Thank you guys and have a great day ahead.